The sea surface topography, or shape of the sea surface, is of interest because it changes continually due to many different physical processes. We all have in mind the ocean tides, but there are other processes that also alter the surface. A few examples are the large current systems like the Gulf Stream, the eddies shaped by these large currents, or the storm responses. It is important to monitor the sea surface height for scientific and societal applications like the focus of ocean currents, climate research, ship routing, cable laying and oil production, as well as management of fisheries, hurricane forecasting, or tracking of debris and plastics, among others.
We want to investigate the use of satellite navigation signals, also called GNSS, reflected off the sea surface, to measure the surface topography very precisely. This is done at very slant geometries, also called grazing angles. So the waves and roughness of the surface have little impact on the reflection process. Then we call it coherent scattering, and the surface acts like a smooth mirror. In a mirror-like reflection, the phase of the signal can be tracked. It is continuous. Different surface heights result in different phase measurements. It gives a very precise measure of the surface altitude at a few centimeters level. The use of two different signal frequencies provides more robust information and permits experimenting with combinations of these two signals.
The European Space Agency funded an activity to investigate the grazing angle GNSS reflectometry technique. An experimental campaign was located at 1,400 meters above the sea level, at the highest peak in the Balearic Islands, the peak Puigmajor, a few kilometers from the coast. It was installed with military facilities, which provided electricity and security. A dedicated GNSS receiver and a set of antennas were installed at the site to collect GNSS signals reflected off the sea.
We developed an instrument to collect the GNSS signals that reach the antennas and store them almost with no manipulation. These signals are recorded 80 million times every second, and this needs more than 1 terabyte of storing space every hour. Once at the lab, we can investigate different ways of processing these signals and optimize the altimetric precision.
Furthermore, an oceanographic buoy was deployed at the measurement area to monitor waves and wind, and thus study its role in breaking the coherence of the signal.
After processing the signal and applying a set of corrections, it is possible to obtain the sea surface height measurement. DIR provided the atmosphere corrections. The GNSS altimetry precision obtained in this experiment is at 3 to 15 centimeter level, which is comparable with dedicated satellite missions in the same region. We have also found the relationship between the sea state and the applicability of this technique. This is an important result for the implementation of this technique in future satellite missions.
These results are also relevant to the European Space Agency PRETI mission, a small satellite for grazing angle GNSS altimetry. This activity was conducted by the Institute of Space Sciences, Institute of Space Studies of Catalonia, the Mediterranean Institute for Advanced Studies, the Coastal Ocean Observing and Forecasting System located in the Balearic Islands, and the Institute for Solar Terrestrial Physics in Germany.